All right. So today I want to explain another paper of Professor Stefan Ehrman in Stanford University. You know, I love all of his papers, and they give us very good insight on. First of all, what is important. We understand what is important. What are the research gaps? We understand how to look at the problem. We understand how to read papers, how to criticize papers, how to write a good terminology. So we learn many things from papers of Professor Stefan Ehrman. Maybe one of the most genius guys in computer science today. There are also other guys like Professor Bernstein in Oxford, Jackie Tomikola in MIT, and many people in Oxford University, Cambridge University. But this paper is about improved techniques for training score-based generative models. So score-based generative models can produce high-quality image samples. First of all, when you want to compare papers, first you should see the goal is, for example, high resolution. Another goal is avoiding mode collapse. Another is fast sampling in diffusion. Fast sampling. So GANs, for example, diffusion has high resolution and avoids mode collapse, but doesn't have this fast sampling. So there are approaches that you can read paper of Stefano Ehrman in 2025, IMM, implicit moment matching, that he used this RST, this triple, to make a very fast sampling approach, and he used MMD for that. So score-based generative models can produce high quality. So here, high resolution is important. As I said, comparable to GANs without requiring adversarial optimization. However, existing training procedures are limited to images of low resolution and can be unstable under some settings. It provides a new theoretical analysis of learning and sampling from score-based models in high-dimensional space, explaining existing failure modes and motivating new solutions that generalize across datasets. So these are the generated samples on datasets of decreasing resolution. So, you don't need background, what is Langevin dynamics. We have talked about it several times. And what is score-based generative models. I have a playlist for denoising score matching, so you can get used to these formulations and problem. And for example, this reference proposes to estimate the score function of each P by training joint neural this score called noise conditional score matching score network, where all expectations can be efficiently estimated using empirical averages. And this is the annealed Langevin dynamics. So it's just a recursive update. So because you have learned a score, so you can update. And choosing noise scales is very important. I've explained it in different videos. So there are many noise scales that you can use. So this paper is a bit engineering. It talks about this technical issues configuring annealed Langevin dynamics. For example, to gain theoretical insight, annealed Langevin dynamic connects two adjacent noise scales by initializing the Langevin dynamics with samples obtained from p sigma I minus 1, another scale. So they have some theorems, and so because this paper is about improving the performance, so for example here we want to improve stability with moving average. Because unlike GANs, these generative adversarial networks, unlike that, score-based generative models have one unified objective and require no adversarial training. So it's very exciting. However, even though the loss function typically decreases steadily over the course of training, we observe that generated image samples sometimes exhibit unstable visual quality, especially for images for larger resolutions. So this issue can be easily fixed by using this exponential moving average. I mean, this is very popular if you want to do algorithmic training in a hedge fund company. It's very important in finance. So if you update this after each optimization step, and M is just a momentum operator. So the conclusion, motivated by both theoretical analysis and empirical observations, we propose a set of techniques to improve score-based generative models. Our techniques significantly improve the training and sampling processes, leads to better sample quality, and enable high-fidelity image generation at high resolution. Although our techniques work well without manual tuning, we believe that the performance, much research in diffusion, score matching, flow matching, Schrödinger bridge, stochastic interpolant, and lots of these ideas. Recently, for example, any order autoregressive mask diffusion, or many new ideas like planned diffusion. All of these ideas, if you look deeply, for discrete data, they have done it only for language, and so you can use all of these ideas for graphs, because graph is completely different thing. It's not a modality, it's a completely different thing, because it has a structure. You cannot put a noise on that, because the sparsity, the topology, everything changes. So, there are a few papers still, and because there are a few conferences that are relevant to this, only ICLR, NeurIPS, and ICML are relevant to this sort of thing that I like. So that is an interesting research gap, that you can apply all the things for the graph generation. And graph generation can be hierarchical, because most of the papers I see are at the level of atoms and edges instead of higher order things. Still there are papers, but there are 5% good papers on higher order structures.